Okay, well, thank you for inviting me today. So I'm going to be talking about how I've used Bayesian networks to impose structure on unstructured data that has a low amount of linguistic resources available for it. And in this talk, I'm going to present work that I've done on two projects. So my dissertation work on learning verb syntax in biomedical text, and my current work on the Babel project, learning morphology of low resource languages. Then I'm going to return to my dissertation work and talk a little bit about some of the design decisions and obstacles we encountered in writing a graphical modeling toolkit to facilitate that research. And I'll conclude by just some broad research priorities and how I see them relating to the work that's going on at the center right now. So, learning verb syntax for biomedicine. There are really two motivations for this research. The first aspect is pretty straightforward. Biomedical text is growing at an exponential rate. The figure on the left represents the number of articles that is in the largest publicly available data set of biomedical journal research journals. And over the past 10 years, it's been growing at about 1 million articles per year. Medical professionals need to be able to access this information. They need access to the latest research for either their own research or for their clinical practice. And it's just not feasible for them to digest it directly by reading all of the articles in their field. That's where biomedical text processing, or BioNLP, comes in. It can facilitate access. It can add structure to the data in various ways. So it can do things like indexing for search engines, building databases of important entities and relationships, and even go as far as to detect new causal relationships in just by looking at the research text. The figure on the right shows the data growth and user growth of one of the larger gene databases that the National Library of Medicine maintains, and you can see that there's a high demand for this kind of structured information coming out of biomedical text. Even though it's widely recognized that biomedical text is a very important area to research, it's being treated mostly as a single monolithic domain. Most of the kind of curated resources that we have that we would train models on or evaluate results on are drawn from a pretty narrow corner of this data, in particular molecular biology and genetics, and often just looking at some subset of those, like a particular genetic disorder or even just the abstracts of articles. So one of the first things that we did was we performed a broad study of linguistic variation across different biomedical subdomains. I won't show the actual results from that study now, but we found nearly universally significant variation between all the pairs of subdomains that we looked at for pretty much all of the feature sets we looked at. And these were feature sets like distributions over part of speech tags, over syntactic structures, some distributional semantics, lexical features, and so forth. So that's one aspect of the motivation. The other aspect of the motivation is verb syntax. Why do we care about verb syntax in particular? It seems like a very specific phenomenon to care about. Well, the reason is that verbs govern the structure of a sentence in a way that the other parts of speech do not. So you can imagine that if you saw just the word explain in a sentence, you didn't know anything else about the other components of that sentence, you already know quite a bit about the sentence just based on your knowledge of that verb. So, for example, you know that it has to have a subject, you know that it probably has a direct object, and you know that it probably has an indirect object. And you also know some semantic properties of these things that come out of this, of knowing what the verb explained means. So you know that the subject is going to have some sort of ability to give an explanation. You know that the direct object is going to have some sort of information content, some sort of an abstract idea, and you know that the indirect object has to have some sort of cognitive ability that lets it receive information. And verbs can occur with different configurations of arguments. And we're going to call these different configurations of arguments frames. So the most familiar examples would be something like transitive and intransitive. some verbs can or cannot occur with these frames. So they died is valid, intransitive. They set is not. It seems to be in need of an additional argument. And then the converse is true when you look at transitive. And then syntax and semantics interact in some strange ways. So if you look at these two sentences, the cake baked in the oven and the chef baked in the kitchen, at a certain syntactic level, they're identical, but they have very different semantic interpretations that you would need to know properties of the verb to really grasp. Now in this talk, I'm going to be focusing on learning syntactic frames, but it's not really a clear line. It's very hard to disentangle syntax and semantics when you're looking at verbs. So if we were looking at this sentence, we could consider the verb explained to be taking several different types of frames, depending on how fine-grained we want to be. So we could say that it's occurring with a noun and a preposition. We could say that it's occurring with a subject, a direct object, an indirect object, or we could go even further and include some almost like semantic roles and have speaker, idea, and listener. So where we draw the line and what we call a syntactic frame is going to be a bit of a gray area. Since I'm going to be using unsupervised approaches, I'll largely sidestep this by just providing it syntactic features for the purposes of learning, and then let it construct its inventory of syntactic frames based on that. So that's how we'll control there. And knowing verb syntax is particularly important in biomedicine because biomedical text processing often involves extracting entities, relationships, and events. And verbs are very important to this. So you can see that in this example, if the verb comes from this set of verbs under activate, we know something about the subject that's probably a protein, and we know something about the direct object that's probably a gene. And of course, the particular verb is going to tell us something about that exact relationship that we've, so if we're trying to create a database of these things, either the entities or the relationships, it's going to be very crucial that we understand how the arguments relate to the verb. Based on what we've seen of linguistic variation in other in kind of broad linguistic features, we were concerned that this also might be an issue for verb syntax, and so we also did a preliminary study of this on a verb-by-verb basis across different pairs of subdomains. And we found that there are two ways that, there are two types of novel syntactic behavior that you really see when you go to a new subdomain. So sometimes a verb will take on a specialized usage, like if you think of activate or express in genetics. But also subdomains frequently coin completely new verbs, like phosphorylate. And these are very subdomain specific. We don't know what arguments correspond to these verbs. And you really need a domain expert to come in and tell you how to interpret this particular relationship. It's very technical. So the third preliminary study we kind of did here was to look at what resources there are for learning syntactic frames currently. And so the existing state of the art for this is we looked at two systems, Valex, which is developed for general language, it's trained on Newswire data, and the Biolexicon, which, as the name implies, is targeting verbs in biomedicine. And they both follow the same basic pattern. They apply kind of a preliminary parser, base parser, to the sentences to get some guesses of what the arguments are to the verb. They then extract the kind of candidate syntactic frames from the parse tree output. They aggregate the frame by verb counts, and then they normalize them to get probability distributions, and then apply some sort of threshold to filter extremely low frequency combinations of verbs and frames that they believe might come from parse errors. And this shows, so we looked at how these performed when we ported them to biomedical text. The first row here shows Valex in its native domain of Newswire with an F-score of 65, so we consider that to be a state-of-the-art performance. And you can see that it drops off precipitously when you go to biomedicine. So Valex does very poorly when we go to specialized subdomains. The Biolexicon makes up quite a bit of this difference. But but it's still underperforming. And an important thing to note about both VALEX and the BioLexicon is there are large hidden costs to both of these systems. Sorry.
Can you explain what the task is? I didn't get the idea.
Okay, sure.
So are you trying to get the frame of every verb instance, or are you trying to figure out all the frames of a verb?
We basically want to learn a verb's probability distribution over possible syntactic configurations.
Okay. And do you assume that the configurations are known, or discovering that is also part of it?
Discovering that is part of it. Well, I can go into the details of how these two systems work.
I just want to know how to interpret these numbers. What does an F-score mean? What does precision mean?
Okay, yeah. I believe that these F-scores are based on type-based token, type-based frame recall. So basically it's saying, making a hard decision about whether a verb can occur in a particular syntactic configuration, right, and whether it's correct or not. Okay. So that's what these numbers are. It's not a great evaluation, but this is what this is what they were doing when we.
Right.
When
so
we
if I had, let's say, 500 verbs, then there are 500 test samples, and each verb, let's say, can occur in 7 frames.
Right.
And you hypothesize 5 of them correctly, and you hypothesize another 4
right,
that it doesn't appear in.
Correct.
Then your recall is 5 out of 7, and your precision is 5 out of 9, and the F-score comes out.
That's correct. Yes.
So each verb is a test sample.
Yes. Yes. Yes.
So another question. So is there gold standard parse trees for this data? Do you know?
No, they're not gold standard parse trees.
Okay.
This was, I think, the Newswire was the BNC corpus. I don't think there are no parse trees for that. And
okay.
So one thing I'm going to say about the drawbacks of these two systems is they both use different parsers that are just applied to this data. That there's no gold standard for the data they're actually training on. So they parse this training. The parsers are trained, of course, on something.
Do you know what they're just Wall Street Journal?
Well, that's one of the important things here is that the VALEX parsing system is unlexicalized and it's just trained on. I believe it is Wall Street Journal.
Okay.
So that is kind of a Newswire, but general language, unlexicalized parser. The BioLexicon is trained on a whole hodgepodge of different, whatever tree banks they can get, basically including the Genia tree banks, which are biomedical text, drawn mostly from biochemistry. And that's, we believe, why BioLexicon does so much better, and it's a lexicalized parser, so it actually already knows something about verb-specific probabilities, which is kind of cheating.
So what do you mean by lexicalized versus, are you just referring to like the Collins model versus a plain PCFG or something?
Yeah, exactly.
Okay,
yeah.
All right.
So the VALEX, you would expect the VALEX system to, not get as high quality parsing out of it, but to at least be unbiased, with respect to what a particular verb is going to have, to the particular verb's probabilities over syntactic configurations, right? So it just has the kind of general verb notion of a verb is here, what is it going to expand to? So BioLexicon kind of knows a bit about the task before it even begins, so it's a little strange. And it's also very expensive to produce the tree banks that BioLexicon depends on to get this much higher F-score. VALEX also has a drawback, which is that it uses a rule-based system for extracting the syntactic frames from the trees. And these are Lisp syntax rules that are very arcane and were developed by linguists and computer scientists sitting down together for a year and writing out a whole list of all the possible syntactic frames they thought existed. So that was also very expensive to produce. So these systems both rely on some kind of hidden costs. So that's the important point there. So to summarize these motivations, we're interested in biomedical text because it's growing rapidly and shows a large amount of linguistic variation. Verb syntax is important because it adds structure to the text. And the existing methods are inadequate because they have mediocre performance when we port them to biomedical text, and because they require expensive human effort to even get to that level. And so we think that we needed a data-driven method for learning verb syntax that we could apply to new subdomains. So the goals for our new approach were that we didn't want to depend on expensive training resources. We didn't want to be tied to a particular formalism or feature set, and we didn't want to pre-specify the possible syntactic frames. Those two are kind of tied together in the VALEX system because, like I said, they have these handmade rules that actually refer to the particular formalism of the parser that they're using. And a little more abstractly, we wanted to make it possible to wire in other linguistic phenomena, because like I mentioned, syntax and semantics are closely related when you're looking at verbs, and we thought we might want to get some benefit out of trying to learn both alongside each other. So we decided to go with Bayesian networks as our framework. I assume that I'm not going to go into describing what Bayesian networks are that deeply. I'll just say that we start with observed data, which are the double circled nodes. We specify causal relationships and kind of probabilistic structure between the variables. And this essentially decomposes a complex distribution, a potentially complex distribution that's global over all variables, into a composition of many simple local distributions over subsets of the variables that are much easier to reason about. And the graph tells a story about how the observed data was generated. Now, in our case, the observed data is going to be instances of verb and some set of syntactic observations. I call them syntactic observations. These are really arguments, what I called arguments before. Just calling them syntactic observations because we want to be a little more vague in what that actually is and experiment with different choices for how we fill that in. So we're going to fill that in, the syntactic observations, for a given verb instance. There are two ways that we can, there are two stages to defining what constitutes a syntactic observation for a verb instance. First, we have to decide what other locations in the sentence are going to be relevant to that verb or potentially relevant to that verb. Then we have to decide what about those locations we're going to extract to be the kind of identifying information for that value. So one possibility following the state-of-the-art systems is to just use this, an unlexicalized parser and look at the parse tree and follow the dependencies, in which case we would get these two locations as relevant for this instance, the verb run. Then we choose what about the location to extract, and we could stay we could be general or specific. We could just extract the parse speech tags, in which case we would say that run is occurring with a pronoun, a plural pronoun, a singular noun. We could extract the grammatical relation, in which case we'd say it's occurring with a subject and a direct object. We could combine the two, and we could even lexicalize it a bit by just function words, because again, we're trying to avoid putting too much semantics in this model, although it's hard to completely isolate it. The other situation is where we don't have any parse input to begin with, in which case we can just choose our syntactic observations based on a window around the verb. And so if we had a window of 3, these are the locations that we would look at. And then do something similar in terms of extracting what information we want to actually use to constitute the frame. And so using the offset and the tag, lexicalizing by the function words. So these are the possibilities that we experimented with. So returning to those, to designing the Bayesian network itself, we can use plate notation to condense it a little bit. So we have n instances of where there's each instance has a specific verb and a set of syntactic observations that we believe have occurred with that verb. And we're going to posit some latent structure that explains how these relate together. So this is the verb over frame and frame over observation nodes are going to be sets of categorical distributions. Yes.
Let me back up one slide and ask you a quick question. Maybe one more. So these are sort of two